Hi friends, today let's talk about the transformer architecture from the paper Attention is All You Need. This paper introduced a scalable attention mechanism that has revolutionized multiple fields, including NLP, computer vision, and recommendation system. It is also an important building block for large language models. Here's our agenda today. We will first talk about what attention is like before transformer architecture. Then we will give a quick overview of what transformer architecture looks like. After that, we'll dive into the innovations of attention that transformer architecture has introduced. And then we will compare RNN attention with transformer attention to understand why transformer attention is superior than the RNN attention. And lastly, we'll talk about how transformer has inspired the recommendation system industry. Before transformers, attention mechanisms were usually used alongside recurrent neural networks. Let me explain how it works. So here is an example of using recurrent neural network to do machine translation. It's translating English to French. In this context, here's how a standard RNN works. The encoder processes input tokens one by one, and each hidden state depends on the previous hidden state and the current input. After the encoder processes all the input tokens, it will generate a context vector. This context vector is used in every output generation. As you can see at the decoder time, each state vector takes the previous state vector and takes a global context vector as well as the last output as input. The key limitation here is obvious. We are using the same context for every output token generation. There's just a lack of emphasis on how important an input token is to the output token. RNN with attention improved this by calculating different context vectors for each output token. Let me give an example of how C2 context vector is calculated. Step 1 is to use the previous state matrix as query, and then you calculate alignment matrix by seeing these as your key. So here you get the alignment scores. Notice that RNN with attention, the encoder part doesn't change. You still have to go to this step-by-step process to calculate the hidden state. But here, we are using the hidden state as a key for the attention. We are using the state matrix here as a query for the attention. With that, we get the alignment score. After you get the alignment score, you use softmax to normalize your score into probabilities. That's where you get the attention weights. After you get the attention weights, you also use the hidden states as values. Since we use hidden states as values, we do a matrix multiplication between hidden state and attention weight. With that, we calculate a weighted sum of all the hidden states along with attention weights. And that's how we get the context matrix for position 2. This was a significant improvement because different output tokens can now focus on different parts of the input sequence. So previously we had one single context vector. Now we calculate specific context vector for specific output token. For example, right now, when we are translating this English sentence to French, this word should pay more attention to cat in the input and not the mat. RNN with attention is able to quantify such emphasis using the output-specific context vector. Now, let's look at the transformer architecture that completely changed the game. The transformer has an encoder and decoder architecture, just like RNNs, but with a crucial difference. It uses no recurrence or convolution, relying entirely on the attention mechanisms. Let's break down to the major components. So these are the 4 key components in transformer architecture. We have self-attention, cross-attention, feed-forward network, as well as positional encoding. Both encoder and decoder have almost the same, except for that in decoder, it uses cross-attention. Encoder doesn't need it. Let's take a closer look. The encoder has a set of identical blocks. Each block has 2 main sublayers. One is the multi-head attention, the other is feed-forward neural network. And layer normalization and residual connections are around each sublayer. For the decoder, it's similar. It has a similar stack of blocks, and each block has 3 main sublayers. In addition to the self-attention and feed-forward neural network, for output decoder, it also has this cross-attention. Similarly as encoder, layer normalization and residual connections are around each sublayer. So because transformer doesn't have recurrence, they need some positional information. That's why they have this positional encoding that converts the position integer into the input embedding. These provide information about token positions, and they're deterministic and represent the absolute positions in the sequence. Usually, they're concatenated with the input embedding. Now let's dive into attention in transformers. The transformer architecture introduced 3 key innovations. Let's go through them one by one. First, scale dot product attention. It computes attention using query, key, and value matrix. And then it uses dot product of query and key to measure similarity. So it's here. It scales dot products by dividing by the square root of the key dimension. This scaling prevents dot products from growing too large because of the high dimension of key matrices. After that, it applies softmax to get attention weights. And finally, it multiplies the weights with value to get the final output. Secondly, the multi-head attention. The key idea is to run attention multiple times in parallel with different learned projections. The projections mean these matrices. This way, each head can focus on different aspects of the input. Finally, when each head has learned its own attention, the multi-head attention concatenates the output from all heads and applies a final linear projection. It is very intuitive that with more attention, there's more parameters and model is bigger and more expressive. But also, this way of having multiple attention running in parallel, according to the paper, it makes the model more robust. Next, let's talk about how attention is applied in transformer architecture. There are, on a high level, 2 types of attention. One is self-attention, the other is cross-attention. Within self-attention, encoder directly used self-attention, while decoder used masked self-attention. The difference between self-attention and masked self-attention is that for a decoder, you don't want them to see the future tokens or calculate attention weights for future tokens because it's not available. It shouldn't be available at training time. That is why you apply a mask so that each token can only attend to the previous tokens when calculating attention weights. And cross-attention is a different story. The difference between cross-attention and self-attention is that for cross-attention, query is from decoder and key and value is from encoder. But for self-attention, query, key, and value, they are all from the same source. Here's a table to summarize the difference. So self-attention in encoder, it helps understand the input context. And self-attention in decoder, it understands the output context and generates one token at a time. For cross-attention, it helps the decoder to learn from the encoder. Now let's compare transformer attention with RNN attention. The paper identified 3 metrics to quantify the performance and efficiency of attention mechanism. The first one is computation complexity. Since RNN is n step, its complexity is OND squared. For self-attention, its computation complexity is majority based on the query key alignment matrix calculation, and that complexity is ON squared D. And next is the sequential operations. The less sequential operation it has, the more parallelism it can apply. So because RNN, every hidden state is dependent on the last hidden state. That is why the sequential operation for RNN is ON, but for self-attention, there is no such step-by-step dependency, so everything can be run in parallel. That's why the sequential operation is O1. The next is the path length between positions. This one is used to quantify the performance of learning long-range dependency. Concretely, it means that if your sentence is very long, how good your performance is. And this is quantified by the path length between the first token and the last token. For example, here, in order to have the hidden state of the last token 4, you have to learn step by step from token 1. But for self-attention, since we have this alignment matrix that connects each token with every other token in the sequence, so the path length for self-attention is O1. Here's a summarization. So RN attention is bottlenecked by the sequential processing and the side effect is that it is not able to learn the long-range sequence well. Transformer fundamentally solve this by having this scalable self-attention that can parallel process all the sequence. And this opens the door for transformer attention to be applied in industry. Now, let's talk about how transformer has inspired recommendation system. The reason why we want to talk about recommendation system is not only because it is one of the most mature machine learning system in industry, but also because it is one of the machine learning system that has the most robust business models. Let me show you the 3 key applications. First is the 2-tower architecture. It is similar to having separate encoders for different types of data. In the context of YouTube recommendations, you want to predict whether this user will click on this video. So you will have 2 towers, one tower for user representations and the other tower for item. And each tower generates a vector. We can call it user embeddings and story embeddings or item embeddings. And we can use the dot product of these 2 embeddings to model the probability of user click this item. This is analogous to having 2 separate encoders. The second example is sequential recommendation. In sequential recommendation, we treat user history as input sequence and future interactions as the output sequence. The classic example here is from the paper Self-Attentive Sequential Recommendation, also called SaSRec. This is an application of encoder and decoder architecture from transformers. Last but not least, let's talk about cross-attention. This paper, Deep Interest Network from Alibaba, they creatively applied cross-attention in user item modeling. So their task was to use user history to predict how user will interact with this item. So the query, as you can see, from the candidate item, and keys and value from user history. In recommendation system, they call it target attention, but it is cross-attention exactly. I thought this is a very smart application. It is similarly as cross-attention being applied in decoder. In summary, these applications show how the fundamental ideas from transformers can be creatively applied to solve practical business problems. To wrap up, transformer architecture removed the recurrence bottleneck for scaling. It is therefore widely adopted in multiple fields, including NLP, computer vision, and recommendation systems. I hope this is helpful. Thank you for watching.